Yeah, so how would the neurons in our brains, how would they fire if there is a knock on a door? Clearly, the neurons would reflect this pattern, this model. So if you have a gentle knock, clearly that corresponds to no fear. So you can see the fear level is 0.0. And then as the intensity of the knock increases, what happens? Your fear level will grow. So you have a gentle knock, and then what happens? The fear level is 0. And then as the intensity of the knock increases, what happens? Your fear level begins to grow gradually, up until it gets to, for example, 1. And then if your fear level is 1, what happens? Maybe you would have to seek cover, or you would have to protect or defend yourself. Yeah, so the neurons in our brains react in this fashion. They do not react linearly. You can see there's a linear fashion here. Our brains do not react in this fashion, in a linear fashion. Yeah, so our brains, the neurons in our brains fire in this non-linear approach. And it would make sense to also model this behavior in our neural network. Remember, this neural network we implemented in lecture 6 reflects how the human brain works. So that means for each neuron, we would also have to model this behavior. We will have to model this behavior, and then such that each neuron will reflect that model. So we have an input to this neuron. Before these N3 outputs, it would have to go through this. So they call it the sigmoid activation function. So you can see the sigmoid activation function. Each neuron would have to implement this behavior, because, I mean, in reality, that's how our neurons, that's how they fire. And so let's go to our code. Remember, we did this, implemented this in the previous class. This neural network here, this neural network. And then, so what that means is that we'll have to create a sigmoid function that reflects this behavior. And then each neuron would have to pass through that sigmoid function before the output would move to the next layer. I remember we also did this in lecture 6. I mean, doing the matrix multiplication, the input into the weights, and then the output of that moves into layer L1, and then the output of this would also flow into layer L2. And yeah, so you can see you have the input, and then the input would multiply the weights. You can see, remember, we're using a lone data set. Yeah, so the input here, the input N1 and N2 would multiply the weights, and then you have layer L1. And so that layer L1, before it goes out, it will also have to go through the sigmoid activation function. So the first thing we need to do is to create our sigmoid activation function here, and then call it def sigmoid. And then the function has got a parameter, and then we are returning, want to return the sigmoid function. This is how it looks like. 1 plus 1 pi dot exponential minus x. So I hope this works. Yeah, so this is our sigmoid. And what that means is that once we have an input to L1, so this is an input to L1 now, an input to layer 1. So the input would have to go through the sigmoid function before we have an output that would multiply W7, W8, and W9 in this, in the weights here. Okay, then, so we have the sigmoid function, and then so that means is that we'll have an output from from L1 will look like this. So we'll call our sigmoid, and then call our sigmoid, and then that means we'll pass in this the inputs to that. So there's input, and then it goes through the sigmoid function just to also model how the human neurons, how they work. Yeah, let's see the output here now. Let's bring the output from the neuron, you see. And then let's bring this one. Okay, let's do this one first so you can see. So that's output. So it means that we passed the input to N3 into the sigmoid function, and then the output is 0.5584. 0.5584. We also passed the input to N4 into the sigmoid function, sigmoid activation function, and then we have 0.514. And lastly, we also passed the input to N5 into the activation function, then we have 0.554. So clearly it reflects how the neurons in our brains, how they fire. Yeah, so remember, this neural network also reflects how the brain works. Okay, then, so we can see, let's say the input to L1. So come here, then you can see. So we have the input, so there's the input. And then you can see that we have the output. So this is the input to the 3 neurons before the activation function. And then you have the output after the activation function. The same thing replicated here. So just copy this one, and then we have the same thing here too. So we also replicate the same thing here. So the output from the sigmoid would also have to go through the sigmoid too. So there's a neuron too, so we must ensure that each neuron would have a sigmoid function. So the input to that neuron would pass through a sigmoid function. So we'll also do the same thing here. So we'll have output from L2. So I'll take this one out. Also take this one out. And then we'll have output from L2, and then to be input to L2. So it means there's input to layer 2, input to layer 2, the input to layer 2. Once you do your matrix multiplication, which is on stage 2 here, the output N6 would also have to go through the activation function. So that's what we did here. And then clearly we have an output here. And then we have output, which would, as you can see, the output gives 0.5. Yeah, so without the sigmoid function, our model doesn't reflect how the human brain works. Yeah, so having those sigmoid function would create some non-linear behavior. That's how our brain functions. Our brain, yeah, that's how it functions. The function rather. And then once we have that that model implemented, that behavior would also reflect how the human brain works. I hope this is clear, and I'll see you in the next class.